Hi, in last video we have discussed the conditions we need to know to identify Hamilton path and circuits. In this video we will focus on describing shortest path problems, shortest path algorithm, and the traveling salesperson problem. Many problems can be modeled using graphs with weights assigned to their edges. As an illustration, consider how an airline system can be modeled. We set up the basic graph model by representing cities by vertices and flights by edges. Problems involve distance can be modeled by assigning distance between cities to the edges. Problems involving flight time can be modeled by assigning flight times to edges. Problems involving fares can be modeled by assigning fares to the edges. Figure 1 displays three different assignments of weights to the edges of a graph representing distance, flight times, and fares, respectively. Graphs that have a number assigned to each edge are called weighted graphs. Weighted graphs are used to model computer networks, communications cost, the response time of the computer over these lines, or the distance between computers can all be studied using weighted graphs. Figure 2 displays weighted graphs that represent three ways to assign weights to the edges of a graph of a computer network, corresponding to distance, response time, and cost. Several types of problems involving weighted graphs arise frequently. Determining a path of least length between two vertices in a network. Let the length of the path in a weighted graph be the sum of the weights of the edges of this path. What is a shortest path that is a path of least length between two given vertices? For instance, in the airline system represented by the weighted graph shown in Figure 1, what is a shortest path in air distance between Boston and Los Angeles? Another important problem involving weighted graphs asks for a circuit of shortest total length that visits every vertex of a complete graph exactly once. This is the famous traveling salesperson problem, which asks for an order in which a salesperson should visit each of the cities on his route exactly once so that he travels the minimum total distance. There are several different algorithms that find the shortest path between two vertices in a weighted graph. We will present a greedy algorithm discovered by the Dutch mathematician Kistra in 1959. The version we will discuss solves this problem in undirected weighted graphs where all weights are positive. It is easy to adapt it to solve shortest path problems in directed graphs. Before giving a formal presentation of the algorithm, we will give an illustrative example. What is the length of a shortest path between A and Z in the weighted graph shown in Figure 3? Although a shortest path is easily founded by inspection, we will develop some ideas useful in understanding the Kistra algorithm. We will solve this problem by finding the length of a shortest path from A to successive vertices until Z is reached. The only paths starting at A that contain no vertex other than A are formed by adding an edge that has A as one endpoint. These paths have only one edge. They are A and B of length 4 and A and D of length 2. It follows that D is the closest vertex to A and the shortest path from A to D has length 2. We can find the second closest vertex by examining all paths that begin with the shortest path from A to a vertex in the set A and D, followed by an edge that has one endpoint in A and D and its other endpoint not in this set. There are two such paths to consider: A, D, and E of length 7 and A, B of length 4. The second closest vertex to A is B, and the shortest path from A to B has length 4. To find the third closest vertex to A, we need to examine only the paths that begin with the shortest path from A to a vertex in the set ADB, followed by an edge that has one endpoint in the set and its other endpoint not in this set. There are three such paths, which are A, B, C of length 7, A, B, E of length 7, and ADE of length 5. Because the shortest of these paths is ADE, the third closest vertex to A is E, and the length of the shortest path from A to E is 5. To find the fourth closest vertex to A, we need to examine only the paths that begin with the shortest path from A to a vertex in the set A, D, B, E, followed by an edge that has one endpoint in the set A, D, B, and E, and it is other endpoint not in this set. There are two such paths. We have ABC of length 7 and ADE and Z of length 6. Because the shorter of these paths is A, D, E, and Z, the fourth closest vertex to A is Z, and the length of the shortest path from A to Z is 6. We now give the details of the Kistra's algorithm. It begins by labeling A with 0 and the other vertices with infinity. We use the notion L of 0 of A equals 0 and L of 0 of V equal infinity for these labels before any iteration have taken place. These labels are the lengths of the shortest path from A to the vertices where the paths contain only the vertex A. Because no path from A to a vertex different from A exists, infinity is the length of a shortest path between A and this vertex. The Kistra's algorithm proceeds by forming a distinguished set of vertices. Let S of k denote the set after k iterations of the labeling procedure. We begin with S0 equal phi. The set S of k is formed from S of k minus 1 by adding a vertex u not in S of k minus 1 with the smallest label. Once u is added to Sk, we update the labels of all vertices not in S of k, so that L of k of V, the label of the vertex V at the kth stage, is the length of a shortest path from A to V that contains vertices only in S of k, that is, vertices that were already in the distinguished set together with u. Where W of u and v is the length of the edge with u and v as endpoints. This procedure is iterated by successfully adding vertices to the distinguished set until z is added. When z is added to the distinguished set, its label is the length of a shortest path from A to Z. So finally we have L of k, A and V equal the minimum of L of k minus 1 of A and V and L of k minus 1 of A and U plus W of U and V. The following example illustrates how the Kistra's algorithm works. We will show that this algorithm always produces the length of a shortest path between two vertices in a weighted graph. Use the Kistra's algorithm to find the length of a shortest path between the vertices A and Z in the weighted graph displayed in figure 4a. The Kistra's algorithm to find the shortest path between A and Z are shown in figure 4. At each iteration of the algorithm, the vertices of the set S of k are circled. A shortest path from to each vertex containing only vertices in S of k is indicated for each iteration. The algorithm terminates when Z is circled, and we find that a shortest path from A to Z is A, then C, then B, then D, then E, and then Z with length 13. You can examine figure 4 to see how this path is identified. It is sometimes more convenient to keep track of labels of vertices in each step using a table instead of redrawing the graph for each step. Next, we use inductive argument to show that the Kistra's algorithm produces the length of a shortest path between two vertices A and Z in an undirected connected weighted graph. Take as the inductive hypothesis the following assertion. At the kth iteration, the label of every vertex V in S is the length of a shortest path from A to this vertex. And the label of every vertex not in S is the length of a shortest path from A to this vertex that contains only, besides the vertex itself, vertices in S. When k equals 0, before any iterations are carried out, S equals phi, so the length of a shortest path from A to a vertex other than A is infinity. Assume that the inductive hypothesis holds for the kth iteration. Let V be the vertex added to S at the k plus 1 iteration. So V is the vertex not in S at the end of the kth iteration with the smallest label. In the case of ties, any vertex with the smallest label may be used. From the inductive hypothesis, we see that the vertices in S before the k plus 1 iteration are labeled with the length of a shortest path from A. Also, V must be labeled with the length of a shortest path to it from A. If this were not the case, at the end of the kth iteration, there would be a path of length less than L of k of V containing a vertex not in S. L of k of V is the length of a shortest path from A to V containing only vertices in S after the kth iteration. Let U be the first vertex not in S. In such a path, there is a path with length less than L of k of V from A to U containing only vertices of S. This contradicts the choice of V. So, the first hypothesis holds at the end of the k plus 1 iteration. Now, let U be a vertex not in S after k plus iterations. A shortest path from A to U containing only elements of S either contains V or it does not. If it does not contain V, then by the inductive hypothesis, its length is Lk of U. If it does contain V, then it must be made up of a path from A to V of a shortest possible length containing elements of S other than V, followed by the edge from V to U. In this case, its length would be Lk of V plus W of V and U. This shows that the second hypothesis is true because Lk plus 1 of U equal the minimum of Lk of U, Lk of V, plus the W of V and U. We now state the theorem that we have proved. The Kistra's algorithm finds the length of a shortest path between two vertices in a connected, simple, undirected weighted graph. We can now estimate the computational complexity of the Kistra's algorithm in terms of addition and comparisons. The algorithm uses no more than n-1 iteration where n is the number of vertices in the graph because one vertex is added to the distinguished set of each iteration. We are done if we can estimate the number of operations used for each iteration. We can identify the vertex not in S of k with the smallest label using no more than n-1 comparisons. Then we use an addition and comparison to update the label of each vertex not in S of k. It follows that no more than 2 multiplied by n-1 operations are used at each iteration because there are no more than n-1 labels to update at each iteration. Because we use no more than n-1 iterations, each using no more than 2 multiplied by n-1 operations, and we have Theorem 2. So Theorem 2 is basically saying the Kistra's algorithm uses big O of n to the power 2 operations, addition and comparisons to find the length of a shortest path between two vertices in a connected, simple, undirected weighted graph with n vertices. And this is really an expensive time. We now discuss an important problem involving weighted graphs. Consider the following problem. A traveling salesperson wants to visit each of n cities exactly once and return to his starting point. For example, Suppose that a salesperson wants to visit Dublin, Bray, Waterford, Cork, and Newport, and you can see that in figure 1. In which order should he visit these cities to travel the minimum total distance? To solve this problem, we can assume the salesperson starts in Bray because must be a part of the circuit, and examine all possible ways for him to visit the other 4 cities and then return to Bray. Starting elsewhere will produce the same circuit. There are a total of 24 such circuits, but because we travel the same distance when we travel a circuit in reverse order, we need only to consider 12 different circuits to find the minimum total distance he must travel. We list these 12 different circuits and the total distance traveled from each circuit. As can be seen from the figure, the minimum total distance of 458 miles is traveled using the circuit Bray, then to Waterford, then to Cork, then to Newport, and then to Dublin, and then to Bray, or its reverse. We just described an instance of traveling salesperson problem. The traveling salesperson problem asks for the circuit of minimum total weight in a weighted, complete, and directed graph that visits each vertex exactly once and returns to its starting point. This is equivalent to asking for a Hamilton circuit with minimum total weight in the complete graph, because each vertex is visited exactly once in the circuit. The most straightforward way to solve an instance of the traveling salesperson problem is to examine all possible Hamilton circuits and select one of minimum total length. How many circuits do we have to examine to solve the problem if there are n vertices in the graph? Once a starting point is chosen, there are n-1 factorial different Hamilton circuits to examine, because there are n-1 choices for the second vertex, n-2 choices for the third vertex, and so on. Because a Hamilton circuit can be traveled in reverse order, we need only to examine n-1 factorial divided by 2 circuits to find our answer. Note that n-1 factorial divided by 2 grows extremely fast. Trying to solve a traveling salesperson problem in this way when there are only a few dozen vertices is impractical. For example, when we have 25 vertices, a total of 24 factorial divided by 2, and this is approximately 3.1 multiplied by 1023 different Hamilton circuits would have to be considered. If it took just 1 nanosecond to examine each Hamilton circuit, a total of approximately 10 million years would be required to find a minimum length Hamilton circuit in this graph by exhaustive research technique. And this leads us to another notation that we use in those slides. Big O notation, which can be used to express the complexity of an algorithm or a computation time, as shown in figure 7. For a problem of size n, where we have a constant time, we say the order of 1, and we say the problem has big O of 1, which is the time required to finish the algorithm from execution. A linear time is order n, and this basically is going to be big O of n. We have also when the time is a quadratic time, and this is basically the order n squared, where we have big O of n to the power 2. The exponential time, which is the most expensive one, where we have an order constant to the problem size, and we have big O of c to the power n. As you can see from the figure, this is really an expensive time for a computation device. The time to compute the Kestra's shortest path algorithm takes big O of E multiplied by the log of V, where V is the number of vertices and E is the total number of edges, and we know from previous slide and the previous theorem that this is big O of n to the power 2. The traveling salesperson problem takes exponential time, As the size of the problem increases linearly, the time to solve the problem increases exponentially, where we have big O of c to the power n, which to find the shortest route from vertex A to vertex A, which visits all points and returns to point A. By now, we should understand how difficult it is to find the shortest path in undirected graph. In next video, we will take more example about finding the shortest path in undirected weighted graphs. Thank you and see you in the next one.